Hello everyone and welcome to the second math crash course for OpenGL. Today we're going to be looking at matrices. Last time we looked at vectors, which we can consider as 1D collections of elements. So if you looked at a vector, you just had A, B, C, and now there was only one dimension to that. So you could only go one way. With matrices, however, it's going to be a 2D collection. So we're going to have columns and rows. It's going to be kind of like a table. So you could have something like A, B, C, D, E, F, G, H, I. Something like that. And the way that we're going to represent this is just using, usually you use a capital letter. So it's going to be like, say, the matrix A, or let's actually just have another row in there. So we're going to characterize this matrix by its dimension. So in this case, we have what's called a 4x3 matrix, and that's going to be rows by columns. And as for the elements themselves, we're going to index each element using A at ij is equal to the ith row and the jth column. So it's kind of like indexing into a 2D array. So for example, if we said, but this time the indexing starts at 1. So A, 2, 2, 3, so that's row 2 over here. Column 3 right here, so that's is equal to F. So that's pretty much just how matrices are indexed. Now what can we use these for? Well, we're going to see how we're going to use them in graphics. These are going to be the basis of pretty much everything we do in our environment. So we'll be moving objects with these, we'll be transforming objects, we'll be shading, we'll be creating the colors, and we'll be essentially putting objects on the screen. We'll be doing different perspectives. We'll essentially be constructing our environment using matrices. So we'll first talk about the operations that you can do, and then we will get into how we use them in graphics. So for the first part, we'll talk about the matrix scalar operations. So for multiplication and division, it's pretty simple. You just multiply or divide each element by the constant. So for example, if we had our matrix A is equal to, I'll just use a 2x2 for now, so A, B, C, D. The factor K times A is equal to KA, KB, KC, and KD. So pretty simple there. Now for addition and subtraction, there are two different ways you can do this. You can either add or subtract the factors to every element. So if we had K plus A, using the same example of up here, we would have it's A plus K, B plus K, C plus K, or D plus K, or those would be the elements in one way. Or you could think of it as doing A plus K times I, where I is an identity matrix, and the identity matrix is a square matrix. So square matrix meaning the number of rows and number of columns are the same. So I n, so I sub n is just the n by n matrix with the ones in the columns. We're going to look at why this is so important in graphics. This will kind of be, this matrix right here will be where we start all of our transformations. So the second way you can think about it is multiplying the identity matrix by the factor and then adding that. So this would be matrix A plus, this will be I2 for the 2x2 identity. So A plus 1, 0, 0, 1, which is equal to A plus 1, B since it's unchanged, C unchanged, and then D plus 1. So this way is more used in linear algebra stuff, specifically with finding eigenvalues. We don't really care about that for graphics, but it's just good to know that this is the second way that you can do that. Okay, so that's matrix scalar operations. Now for matrix vector operations, or sorry, matrix, we'll start with addition and subtraction, which once again is pretty simple. So if we have the matrix A is equal to A, B, C, D, and B is equal to E, F, G, and H, A plus B, we're just going to add the corresponding elements. So here the restriction is the dimensions have to be the same. So these are both 2 by 2, therefore we can add them together. If it was a 3 by 2 and a 2 by 2, you could not do that. The operation is undefined. So the resultant here will be A plus E, B plus F, C plus G, and D plus H. And then subtraction would just be the counterpart where you do A minus B, and you just subtract the corresponding elements. Simple there. Now for matrix multiplication, unlike vector multiplication, which was defined in two ways, the dot product and the cross product, there's only one definition here. And so matrix A times the matrix B. Now we're first going to start by talking about matrix vector multiplication, because this will be a good segue into how we multiply matrices. So for matrix vector multiplication, the way to think about this is that we have to consider vectors as either column or row matrices. So the vector, and typically for graphics we will consider it as a column matrix. So if we had a vector V, which was in ND space, so in Rn, which is just n dimensions, we would have the V is equal to V1, V2, all the way to Vn with n elements, and we can consider this as an n by 1 matrix. So we have n rows, V1, V2, all the way to Vn, and 1 column, since there's only 1 element per row. Now when we multiply a matrix by this, so let's say we have our matrix A. Now the restriction here is that A has to be it just has to have n columns. So m by n. I'm going to state this now, but when we do matrix multiplication, the condition for this is that if we have a matrix A which is m by n times the matrix B, which is p by q, the condition here is that this only exists if n is equal to p. So the number of columns in A is equal to the number of rows in B. And we're going to see why starting with the matrix vector multiplication. So if we consider the matrix A as a collection of row vectors, so we have, I'll just denote the row vectors using R. So R1 for row 1, R2 to Rm. So we have m rows, and just think of it as just a bunch of row vectors stacked on top of each other, just like that. So if we had R1 is equal to R11, R12, all the way to R1m, because once again, or R1n, because we have n columns, this is going to be equal to R11, R12, all the way to R1n. And we have R21, all the way to R2n. And then at the bottom, we have Rm1, all the way to Rmn. So m column, or m rows, n columns. So now when we multiply the matrix A times the vector V, well, the way we're going to look at this is a collection of row vectors, so R1, R2, all the way to Rm, and we have our vector, which can have more rows, so we'll do V1, V2, all the way to Vn, and n does not necessarily have to be m, because it's once again just a constraint on the number of columns of the left-hand side. So this is the left-hand side matrix is A, and the right-hand side is B. And we'll see that this makes this operation non-commutative, meaning A times B does not usually equal B times A. So the resultant here will just be the dot product of the vector with each row. So the first row will be R1 dotted with V. Second row will be R2 dotted with V. All the way down to the mth row dotted with V. And we're using the dot product here from what we learned in vector multiplication. So if we were to expand this out, we would get that the first row is R11 times V1 plus R12 times V2 plus all the way to R1n times Vn. And now you see why there was this constraint on the number of columns in the left-hand side matrix, because this dot product will not be defined if there are more more rows in the vector than there are columns in the matrix, because then there will be leftover elements. And then we can do this for the other rows. I'll just do the last one. So Rm1 times V1 plus Rm2 times V2 plus all the way to Rmn times Vn. So that's matrix vector multiplication. And this will be one of the most important things that you have to understand, or at least the mathematics behind how this works. So let's generalize this from matrix-matrix multiplication. If we have our general matrices A and B, where A is the same as above, m rows by n columns, and we're going to have n rows in B, but the number of columns is now going to be generalized. It's going to be n by q. So this restates the rule that we have above, where the number of columns in the left-hand side matrix A must be equal to the number of rows in the right-hand side matrix. So we see here that the n and n will match up, and then our resultant matrix C is going to take the dimensions, these outer ones here. So n must be equal to n, and then our resultant will be m rows by q columns. And you'll have to take that as fact now, but we are going to show how that's going to work. So as with the matrix vector multiplication, we are going to consider A as a stack of rows. So we'll have R1 as its own row all the way down to Rm. Now for B, well, if we know how to do matrix vector multiplication, where we considered a vector as a column matrix, why can't we just generalize that by putting a bunch of column vectors next to each other? So let's try that. We'll use B and we'll have a bunch of column vectors as the representation here. So C1 all the way over to CQ, and that's just defined by the dimension n by q. So we have q columns here. Let's just look at what the result of, maybe we can try and, if we're just stacking for the right hand side matrix, if we're just stacking columns, why isn't the result just stacking a bunch of matrix vector multiplications, or putting a bunch of matrix vector multiplications next to each other? So we have the dimensions here as m by q, so obviously we're going to have m rows, which looks very similar to the matrix vector multiplication, but q columns, that's just going to come from the matrix B. So if we can look at this here now, the result will just be A times C1 as the first column. And that's a matrix vector multiplication. And then we have A times C2 as the second column, all the way over to A times CQ, which is going to be the qth column, or the last column. So we see now that this result is going to have q columns. And I could do all the dot products out, but it's going to be the same as what we have up here. So if we consider each column as a collection of, if we consider each column as V1 all the way to Vn, you'll see that if you just input those numbers into each column, that's what you will get. But, so we have q columns because there are q matrix vector multiplications, but for the number of rows, it's going to be the same as with the matrix vector multiplication. We're going to have m rows here. So with B, each column vector has n elements in it, and that n matches the number of columns here in A. So the dot product is defined for a row of A and a column of B. So if we want to do a general definition for each element of the product, so we often define matrices using this notation here, where we do a square bracket around a lowercase letter A, B, and this is going to be ij for the ith row in the jth column. And you can often use this notation if the element at the ith row and jth column is defined by its position, by its indices. So here it is actually. We take the ith row from A, so Ri dotted with Cj. And this definition here is consistent with what we had in the drawing. So if we look at just AC1, maybe I'll just look at AC1 here. This is going to be equal to so the first element will be the first row, so R1 dotted with C1, and then we have R2 dotted with C1 again, all the way down to RM, sorry, dotted with C1. Note here how this is exactly what we had for matrix vector multiplication, where we have a column vector as the right-hand side matrix, and this column, or the vector product here in this column, stays constant. It's going to be that first column, and then AC2 will be the same thing for general ACJ. So for the jth column, this is just going to be the same row vector R1 dotted with CJ, the jth column, and this will go all the way down to RM dotted with CJ. And that's how we define this product generally. Okay, so those are the basic matrix operations. Now for how this can actually be integrated into graphics. So how are we going to use matrices in graphics? Let's first talk about how we used vectors. So for vectors, so in graphics, for vectors, we add positions. So let's say our position, and I'll just use vector x is equal to x, y, and z. It should come as no surprise to you that since we were talking about matrix vector multiplication, maybe we're going to try and multiply this vector by a matrix to do some sort of transformation. And by transformation, I mean translation, so moving the vector, or rotation, or scaling of the vector. So if we take a matrix A and multiply it by x, we're going to get an output of y, which is essentially our transformed vector. Now in more graphics terms, we're going to represent our transformation matrix as T times a vector x is equal to x prime, or the transformed vector. And if we look at the dimensions here, we already did this, but if x is has n or 3 elements per se, and we want the output to also be in the same space. So this makes sense here, where if we transform a 3D vector, we want it to stay in 3D space. Well, the way to do that is we just have, so if the output is 3 and the input is 3, then if you stare at this long enough, you're going to see that the transformation matrix has to be a square matrix, and it has to be 3 by 3. And if we look at this, we do a t times an x. T is 3 by 3, x is 3 by 1 as a column vector. The 3's in the middle match up, and then on the outside we have a 3 rows by 1 column as the result, which is exactly what we want. So T is our transformation matrix here. And we'll see that each type of transformation has its own special matrix. So we'll start with scaling. So scaling will be pretty simple. So what matrix? We want x to equal k times x. And now I guess I kind of made a mistake about not talking about eigenvectors, but I mean eigenvectors will not come into play here, but we want the transformation matrix multiplied by some vector x to have the result of just scaling it. And in linear algebra, you would technically call x here an eigenvector with an eigenvalue k, but that's not important right now. The important part is, what do we use t as? Well, if we represented t as a, b, c, d, e, f, g, h, I, and then t times x is equal to x, y, and z, and we wanted this to equal kx, ky, and kz. If you take, if you expand this matrix vector multiplication here, you will find that we're going to get this as ax plus by plus cz in the top, then dx plus ey plus fz, and then gx plus hy plus I times z. And if we want the result to be k's on the elements here, we're going to need the a, so I'll highlight these here. So we want the a, the e, and the I to equal k, and then everything else to go to 0. So we need the b to go to 0, c to go to 0, d, f, g, h to go to 0. So a is equal to e is equal to I, which is equal to k. And then all the others equal 0. And this kind of paints a nice picture of translating matrix vector multiplication into its expansion, just because you kind of just take the elements of the vector and insert them in each row and take that and do the dot product there. So t has to equal the matrix k, or the matrix with k in the diagonal. Now, this may look familiar if you were paying attention a little earlier. What's a matrix that we found, or that we defined as having only elements in the diagonals? It's this identity matrix here. So if we have our matrix as with k's in the diagonals, this is just equivalent to k times the identity matrix in a 3x3 identity matrix. So that's pretty cool. So that's the scaling. But what if I'll take it one step further. What if we wanted to scale it by a different factor in each dimension? So if we wanted t times x to equal ax, by, and cz. Well, if we follow this kind of principle again, if we don't want, in each dimension, we don't want any contribution from, so if I were to expand this again, we would have, or I'll do k1, x, k2, y, and k3, z. If we do our expansion here, again, I'm just going to copy this over because it's the exact same. If we use the same 3x3 transformation matrix, just like that, we see that the same elements have to vanish. So all these other elements that multiply by the y and z in the x row have to vanish. So from this we get that a is equal to k1, b is equal to k2, or sorry, e is equal to k2, and I is equal to k3. So from this, we're going to define scaling now as a vector. So the scale vector, which I will call k with a bar above it for vector, is going to be equal to a, e, I. And that's just the scaling vector. So the transformation matrix will be k1, k2, and k3 in the diagonals, and zeros all else. Okay, so that's scaling. Now for translation, the goal is to have that t times x is equal to x plus, I'll say k again, for now our translation vector, because we want to translate it a different amount in each direction. So I'll just expand the multiplication here, ax plus by plus cz, then dx plus ey plus cz plus fz, and then gx plus hy plus iz. And we want this to equal x plus k1, y plus k2, and z plus k3. Or those scale factors are different for each dimension. Now, if you were to kind of look at this, there's no real way to do this. Because the factors in the result in front of x, y, and z have to be 1. So this is a 1x plus a 1y, or a 1x, a 1y, and a 1z. So therefore, we have to have that a is equal to e is equal to I is equal to 1. But if we were to try and figure out, okay, well then k1 is equal to by plus cz, k2 is equal to dx plus fz, and k3 is equal to gx plus hy. Well, there's just way too many constants in here. We have an undetermined system and it doesn't work out. Or an underdetermined system, and there's no combination that works for every coordinate, because y and z can just change on. We could move the object somewhere else, and this k1 the b and c would be invalid to find this k1. So there's obviously a problem here, and the solution is that we are going to extend the dimension of our vectors representing the position and the vector, or the dimension of our transformation matrix. So we're going to go into dimension 4. That doesn't mean that we're moving into 4D space, or we're moving into an environment with 4D positions. We're still going to stay in 3D positions, but we'll only be taking the first 3 elements of our position vector. So now let's try this. Let's try something different. So if we have Tx, where now T is a 4x4 matrix, X is a 4x1 matrix, and we're going to have X prime as another 4x1 matrix. We're going to see that this is, if we want this equal to X 4x1 plus K, the scaling matrix, or the translation vector, we'll see that the matrix T has to have 1s on the diagonal, and then in the right column, we're going to be putting the values of K. So K1, K2, K3. And why did I neglect a K4? Well, when we are multiplying this matrix by our position vector, we have X, Y, and Z. Well, if we want this, and I'll just put an A for that last value now, we'll see what that becomes. If we want this to equal X plus K1, Y plus K2, and Z plus K3, and then A again, because that's what's going to happen if you do the dot product in the last row. You have a 0 times an X, 0 times a Y, 0 times a Z, plus a 1 times an A. Or I can just put a K4 actually, and we'll see that this just becomes K4 times A. Is that right? Yes, it is. We will see here that A has to equal 1. Because this is X plus, because the result of this multiplication is X plus A times K1 if you do the dot product, and then Y plus A times K2, and then Z plus A times K3, and then in the bottom, if we want K4 times A to equal 1, and we know that A has to equal 1, then K4 also has to equal 1. So this K4 becomes a 1, the A becomes a 1, and what we're left is that this fourth element in all of our position vectors has to equal 1. That's just how the math is going to work out if we want to do translations. So that's how, and you might be thinking, well, okay, if our transformation matrix has to be a 4x4 now, how are we going to adapt the scaling matrix? Because we can't multiply a 3x3 scaling matrix by a 4x1 column vector, position vector. Well, you can simply just expand the scaling matrix and just leave that last element as a 1. So we have a K1, K2, K3, and if we just leave a 1 in that last diagonal there, we're just upping the scaling by 1 dimension. So if we have an X, Y, and a Z, and then a 1, which we found out that A has to be a 1 there, if we do this out, it's just going to become, or if we wanted to figure out what that K4 now has to be in the scaling matrix, we have K1X, which is desired, K2Y, K3Z, and then K4 times 1. And if we want that last element to stay as 1, then K4 has to equal 1. So this K4 becomes a 1. So now our scaling matrix is upped by a dimension, but the only thing is we're just adding a 1 in that diagonal. Everything else is just entering as zeros. So now we have transformation matrices as 4x4 matrices and our position vectors as 4x1 vectors. And then the final transformation is rotation. I'm not going to write it out just because I'm not going to explain it. It's a lot of stuff. I'll put some links down below in the description though. But I can actually show it to you real quick. This is our general rotation around a general axis with Rx, Ry, and Rz as the rotation axis, and then the theta as our rotation angle, and it's going to be this messy matrix here. Okay, so that's rotation. But the power of representing transformations as matrices is really in combining them. Because let's look at this. Let's just use an example. So if we wanted to combine transformations. So for example, if we wanted to first scale an object, then transform or translated it, which we will be often. When we'll see later on is that when we have our objects, we're going to be first scaling them and then translating them, so that you can have one object, you can have your base object that's somewhere, and then you can have the same version of that object that's scaled and translated, so you can have two versions of the same object. So what do we do here? Well, I'll first say right now that the order matters, and that you have to have scale, then rotation, then translation. But we'll just keep we'll ignore for now. But if we wanted our transformation matrix, which is once again 4x4, times the matrix X to equal X prime, which if we wanted to scale then translate, we would say K1X plus A, K2Y plus B, and K3Z plus C. Well, okay, well, first of all, I forgot the last element. That's a 1, because we have to keep that as a 1. Well, let's do this out. We know that it has to be something where T has to be something of the form with the scale factors in the diagonal, and then the translation factors in the right column. Now, is that all? Can we just get away with doing that? And then we have to put that 1 there. We figured that out in both cases. Can we just get away with using the zeros there on the side? If you do this matrix multiplication now and you multiply this times X, Y, Z, and a 1, you will find that it does work because the diagonals contribute to the scaling. And that's the only factor we get from X, Y, and Z in their respective rows. And then the translation gets multiplied by 1, and it just gets added when we take the dot product. So this is really cool because now we have kind of combined matrices to get this desired result here. So we have the K1X plus A, K2Y plus B, and K3Z plus C, and a 1 at the end. Now, how do we find this matrix? We're just guessing right now. We can take, we can set these elements, but what about when we get more complicated and, God forbid I go back to this stupid matrix here. How are we going to figure that out? And it turns out that matrix multiplication that we were doing earlier is exactly this. To combine transformations, if we wanted to do T scale times X and then translate it, that's just a composition of linear transformations. And if you know linear algebra, you'll understand this, but if you don't, you just got to trust me here. We're just multiplying the matrices, and you can kind of see that in the form here. If we represent T as a function, so I'll say, we'll call the the transformation function, let's just call it f. So fs is equal to t scale. So this is fs, a function of a vector x, and this returns a vector. So this is equal to t scale times the vector x, and then f translate, so ft of the vector x is t translate times the vector x. If we do f translate of f scale, because we have to scale it first before translating, so we need to pass the base vector into the scaling function first, what we're going to get is, this is f translate of t scale times the vector x. And this is a vector in and of itself, so if we pass this as an argument into f of t, or the translate function, we just get that this is t translate times t scale times the vector x. So we're just multiplying matrices by each other. And if you take this this scaling matrix here and multiply it by this translation matrix, you will get that it works out to this result here. So that's the heart of that's the heart of combining transformations, is matrix multiplication. And that's going to be super important for when we start doing this in the actual code. But so that's the basis of that. And once again, the order does matter. You have to do the scaling first, then rotation, then translation. So if we were to do this, if we were to combine these generally, we would have t is equal to t translate times t rotation times t scaling, where t sub t is the translation matrix, t sub r is the rotation matrix, and t sub s is the scaling matrix. So you can do that out if you want. If you just want to like pain yourself, go for it. Do that. But the interesting thing is, I don't really care what we get on the left-hand side, but the right-hand side will just be the ABC 1. That's going to be, the ABC is from our translation, and the 1 just has to stay there. That 1 has to be there always. That can't be. And what we'll also find is that the bottom row is a bunch of zeros, which is also pretty cool. So if you do the multiplication out, you should find that this bottom row is all zeros, the bottom right is a 1, and then the right column is ABC as your translations factors. Okay, so that's a crash course on matrices, and that concludes our math crash course. Next, we're going to be actually installing our mathematics library GLM, and then we'll be looking at some of the code, and we'll be translating the stuff that we've done with the matrices and the vectors into code, and we'll be printing out the results. And then from there, we'll just be going forward with then using matrices and vectors as tools. Like I said last time, or I don't know if I said that last time, but we're going to be using these mathematical elements as tools to kind of create our scenes and project them onto the screen. And we'll see that how powerful these will be in creating our application. So yeah, that's all I have for you guys today. Hope you learned something. Hope you enjoyed, and I will see you in the next video where we install GLM and start writing some code. All right, have a good one.